Hi, we're going to start topic 5B, where we're going to talk about the equilibrium constant, which it should look very, very, very similar to what you saw in Chem 108, but now you've actually seen where the equation comes from to relate an equilibrium constant to a delta G. Okay. So follow along in your textbook. So as I said, this will look very much like Chem 108. And the key idea is that the composition at equilibrium is obtained from the value of K by taking note of the reaction stoichiometry. So basically, setting up an icebox will allow you to take advantage of the equilibrium constant and understanding what concentrations and pressures are when you reach equilibrium. So these are just some general reactions that they use as examples. So this glucose going to, can't remember what F is, if it's fructose, but one product, one reactant, the concentration is a ratio. If you're talking about gases, it's going to be pressure ratio. And remember, these are always comparing concentration back to a standard state concentration or pressure back to a standard state in the way we derived our equations. So each of these is always divided by the standard state concentration. So as long as you're working in the units of the standard state, so if we're working in molarity, these would each be 1. You don't have to worry about it. But if you didn't work in the right concentration or pressure units, you'd have to make sure you divided by that standard state. So our standard state for pressure is the bar, and then just the totally generic equilibrium constant. Products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. And now we've added the idea of an activity. So our equations were derived for ideal gases, and then solutions have the same chemical potential as a gas, so you can use the same expression as you derive for a perfect gas, but now we're taking into account that things might not be perfect when we use activity instead of concentration or pressure. So self-test 5B.1 just asked you to estimate the composition of a solution in terms of the fraction of molecules that are B in which you have two isomers, A and B, in equilibrium. And it gives us the delta G standard state. So in our first topic of this focus, we derived this equation, remembering that K is related to delta G at standard state. Our equilibrium constant is B over A. We want to figure out what moles of B over moles of B plus moles of A are in order to have the definition of a fraction. So first I used the delta G, and they gave it to me in kilojoules, so I converted it to joules to be compatible with my gas constant. Delta G was negative, and this negative cancel. So we end up with an equilibrium constant of 2.4. So that's the ratio of B over A. So now if we want to know the fraction, we can just make an assumption. So we could pick anything and we'd get the same answer. If A equals 1, then B equals 2.4 because B equals 2.4 times A. And then that would mean that the fraction is 2.4 over 2.4 plus 1, A plus B, and you get 0.70. And working with the equilibrium constant will just look very familiar. You're going to set up an icebox is what it's saying here. The initial molar concentrations of solutes or partial pressures. Then you're going to talk about the change and define an X, and then calculate the resulting equilibrium values. Depending on how complex the stoichiometry is, you might have a quadratic, might have a cubic, you might have a higher order polynomial. So Mathematica might come in handy. So 5. This is self-test 5B.2, where it asks us in an experiment to study the formation of nitrogen oxides. In jet exhaust, nitrogen at 0.1 bar is mixed with oxygen at 0.2 bars, so your total pressure is 0.3, and the two gases are allowed to come to equilibrium with the product NO in a reactor of constant volume. They give us the K, and they want to know the equilibrium partial pressure of the nitrogen monoxide. So fairly easy one because of how small the equilibrium constant is. So we start out with 0.1 bar and 0.2 bars, 0 nitrogen monoxide. This has to go down, this has to go down. And when one of these reacts, you get 2 of those. So it's a 2x for the product. So when we set it up, our equilibrium constant is equal to 2x squared, because it has a 2 there, and then divided by 0.100 minus x and 0.200 minus x. And if you notice, this equilibrium constant is 10 to the minus 21. So really, this reaction doesn't take place very much. It doesn't react forward very much. We're going to have a very small pressure of nitrogen monoxide. So I'm going to assume that the x in relation to the starting pressures of nitrogen and oxygen is very, very small because the reaction doesn't go very far forward. And then I can just solve for the x here. So when I do that, I get an x of 4.12 times 10 to the minus 12. That's very valid. If I had subtracted that from 0.100 or 0.200 with the sig figs, it wouldn't have made a change. So our assumption that it was small relative to the starting concentrations was valid. And then the pressure of nitrogen monoxide is 2x. So 2 times that number, 8.2 times 10 to the minus 12 bars of nitrogen monoxide would be present at equilibrium. So now we want to think just a little bit more about what it means to have a standard state in relation to our equilibrium constant. So everything in our equilibrium constant always has to be written in terms of pressures if it's gases, because our standard state pressure is a bar, molar concentration if everything's solution. But then we'll talk about this third situation here in a second. So that means when you use this relationship, delta G naught equals negative RT ln of K, if you have a gas phase reaction, then this is really Kp. All of the pressures, all of the reactants and products must be given in pressures if it's a completely gas phase reaction. If you use delta G standard state for a reaction where everything's in solution, then really what you're doing is getting a Kc, because aqueous solutions or any solutions, their concentration would be given in molarity. So your reference state would be 1 molar. So everything has to be in molarity. So when you solve this, the K would technically be a Kc. Here's the tricky one that's a little harder to think about, but for reactions that involve solutions and gases, you must put gases in pressure in bar and solutions in concentration of molarity. So this is really neither Kc or Kp. It's whatever units you need for your gases and your aqueous or whatever kind of solvent solutions. So think about that, and some of the problems you work, I'm sure, will make you use that concept. So if we did want to convert, so sometimes you do want to take a Kp. So maybe if we got a K up here and we wanted to convert it and use it in concentration units, then it's pretty easy to do that, just thinking about if all the gases are perfect, then if I want to convert pressure to molarity, I just use the ideal gas law. Number of moles over volume is molarity. So molarity is pressure over RT. So for our reaction of A plus B goes to C, and you only can convert a K, a Kp to a Kc. You couldn't convert a Kc if you had solutions to a Kp because you don't have gases. So this only works for gases. We're using the ideal gas law. So everywhere you see a pressure, you divide up by RT to get molarity. You pull all those pressures out front, and that's your Kp. So for this particular reaction, Kp times 1 extra RT gives you Kc. So depending on your stoichiometry, you'll have a different number of RTs. I like to just do it this way, just set it up and think about it. You can also use the equation in the book that talks about the change in number of moles of gases going from reactants to products, whatever you prefer. I find this easier. So this is just going through that process of converting a K to a Kc. And then an example. So you can go ahead and do this one. Self-test 5B.3, just to practice. And as I saw in this test this week, and just to make sure that your units are correct. So you'd use an R in 0.08206 liter atmospheres because you're converting, or liter bars, because you're converting back and forth from bars to molarity. So just think about that when you do it and making sure that your units for your R are correct. This little section on the molecular interpretation of equilibrium constants, it's really best discussed after we do chapter 12. Chapter 12 uses statistics to look at what molecules are doing on average to figure out how you could calculate an equilibrium constant. So skip this little section for now, but we'll come back to it in Focus 12. So that's the end of that topic. Note, our next topic is basically Le Chatelet's principle. So I'll come back and do that in a second.